Imagine a journey back in time, not just thousands or millions of years, but billions. There was a moment when everything in the universe, stars, planets, galaxies, and even the matter that makes up our bodies, was compressed into a singular, infinitely dense and incredibly hot point. This singularity marks the beginning of what we now know as the Big Bang, the prevailing scientific theory that explains the origin and evolution of the universe. The Big Bang wasn't an explosion in the conventional sense. It was the beginning of a rapid expansion of space-time itself, a process that has continued for about 13.8 billion years. At that moment of creation, the universe was in a state of unimaginable heat and density. Matter, energy, time, and space all came into existence simultaneously, and the fundamental forces of nature began to take shape. Before this event, there was no time, no space, essentially no universe as we understand it. In the first fractions of a second, the universe expanded exponentially in a period known as cosmic inflation. During this phase, the universe grew from something smaller than an atom to something that could encompass galaxies. This rapid expansion was followed by a cooling period, allowing subatomic particles like neutrons, protons, and electrons to form. These particles collided with incredible energy, forming a hot plasma soup that filled the early universe. As the universe cooled within the first 3 minutes, the first nuclei began to form through a process called nucleosynthesis. The lighter elements, primarily hydrogen and helium, were created during this time. This explains why hydrogen and helium still make up most of the universe's visible matter. Heavier elements, such as carbon and oxygen, would only form much later inside the cores of stars through nuclear fusion. About 380,000 years after the Big Bang, the universe had cooled enough for atoms to form. This process, known as recombination, allowed electrons to combine with protons and neutrons to create neutral atoms, primarily hydrogen. Before this point, the universe was opaque, with photons constantly scattering off free electrons. After recombination, the universe became transparent, allowing light to travel freely. This radiation from the early universe is what we observe today as the cosmic microwave background, CMB, a faint afterglow that permeates the cosmos. The discovery of the CMB in 1965 by scientists Arno Penzias and Robert Wilson provided crucial evidence supporting the Big Bang theory. This remnant radiation offers a snapshot of the universe when it was only 380,000 years old. By studying tiny fluctuations in the CMB, scientists have learned much about the early structure of the universe, its composition, and its subsequent evolution. For the next few 100 million years, the universe entered a period known as the Cosmic Dark Ages. During this time, there were no stars or galaxies, only vast clouds of hydrogen gas. The universe was cold and dark. But eventually, gravity began to pull this gas together, forming the first stars and galaxies in a process called ionization. The light from these early stars ended the Dark Ages, illuminating the universe and creating the first cosmic structures. The formation of stars also marked the beginning of the creation of heavier elements. Through nuclear fusion in their cores, stars forged elements such as carbon, nitrogen, oxygen, and iron, the building blocks of planets and life itself. When massive stars reached the end of their lives, they exploded in supernovae, scattering these elements across space, enriching the interstellar medium and allowing the formation of new stars and planetary systems, including our own. Around 9 billion years after the Big Bang, our solar system began to form. A collapsing cloud of gas and dust gave birth to the sun, planets, and other celestial bodies. This process was driven by the same forces that had governed the formation of the first stars and galaxies. Today, we continue to see evidence of the universe's ongoing expansion, a discovery first made by Edwin Hubble in the 1920s. By observing that distant galaxies are moving away from us, Hubble showed that the universe is still expanding, a direct consequence of the Big Bang. One of the most intriguing aspects of modern cosmology is the discovery of dark matter and dark energy. Dark matter is a mysterious form of matter that does not interact with light, but exerts gravitational influence, helping to hold galaxies together. Dark energy, on the other hand, is thought to be responsible for the accelerated expansion of the universe. Together, dark matter and dark energy make up about 95% of the universe's total mass energy content, yet their nature remains one of the greatest mysteries in science. The Big Bang Theory, while widely accepted, continues to evolve as new discoveries are made. It has revolutionized our understanding of the cosmos, showing us that the universe is dynamic, ever-changing, and far more complex than we once imagined. From the smallest subatomic particles to the largest galaxy clusters, everything we see today can be traced back to that singular event 13.8 billion years ago. Ultimately, the Big Bang is more than just a scientific theory. It is a story of cosmic origins. It tells us that we are all connected, that every atom in our bodies was forged in the heart of stars that were born billions of years ago. In the grand scheme of the universe, we are made of stardust, and our history is deeply intertwined with the history of the cosmos itself. The journey of discovery continues as we probe deeper into the universe, seeking to answer the fundamental questions about our existence and the ultimate fate of the cosmos. Whether through new technologies, advanced telescopes, or daring space missions, humanity's quest to understand the Big Bang and our place in the universe remains one of the greatest scientific endeavors of all time.